And really, there are two main things I want to do in this talk, and if we have time, we'll get to a third. The first thing, I just want to summarize where we've gotten to in fundamental physics now well into the 21st century by reminding you about the 20th century revolutions, which were of quantum mechanics and space-time. And there's this theoretical framework, quantum field theory, that lets us talk about worlds that are compatible with the principles of quantum mechanics and space-time. And the first message, which is, I think, not widely enough appreciated, even among physicists, never mind outside physics, is how these two principles are astonishingly restrictive and largely dictate the grand architecture of physical laws. And really, the beef of fundamental physics is really constantly about seeing this tension and resolution of the tension between quantum mechanics and space-time. And these grand principles are never far away from the action when you're working on anything in this business. So that's the first point that I want to make. And that makes all the more jarring the second set of points, which are what the storm clouds are. Again, here we are well into the 21st century. And they have to do with the fact that these astonishingly restrictive and successful ideas are likely to be superseded and replaced with something that might eventually look quite different. So the notion of space-time is likely doomed because of gravity. Because of effects of quantum mechanics and gravity. There may even be limitations to quantum mechanics when we start attempting to apply the laws of quantum mechanics, not to individual experiments, but to the entire universe in quantum cosmology. And closer to home, there's a very simple question. One of the most obvious facts about the universe is that it's big. So the universe is big and it has big things in it, even though it's made out of microscopic constituents with fundamental laws given at tiny distances. So it turns out we have a terrible answer to the question, why is the universe big with big things in it? These two mysteries might even be related to each other. So those are the sort of main storm clouds that are driving work in this subject in one way or another. And as I said, if we get to it, I'll say something about a speculation, which has certainly directed my own research over the last 10 years or so, which is that we'll come to see these grand ideas, these big principles of space-time as quantum mechanics, as actually emerging hand in hand from more primitive mathematical ideas. Okay, so let's get to it. First, let me tell you about space-time quantum mechanics and how these two principles make the grand architecture of physical laws largely inevitable. A quick reminder to those of you who aren't physicists, the world around us is made out of matter. We have atoms with electrons whizzing around protons, protons and neutrons and nuclei. If we look inside the protons and neutrons, we'll see that they're not point-like elementary particles, but they're also made out of apparently point-like constituents. The electron is an apparently point-like constituent. We haven't seen any substructure to it, but the proton and neutron definitely have substructure. And they're made out of point-like constituents that are up and down quarks that are held together inside the proton. They can't get out by the gluons. And we have four basic interactions: gravity, electromagnetism, and the weak and the strong interactions. Gravity and electromagnetism were known to the ancients. The weak and the strong forces began to be known in the very, very late 1800s, early 1900s. The weak interactions are associated with radioactivity. The strong interactions are what hold the earliest incarnation of them was a question of what held protons together in the nucleus of the atom, even though the Coulomb repulsion, the electric repulsion, wants to drive them apart. Today we know that that is a subsidiary effect of a more fundamental set of interactions that act on the quarks and the gluons inside the protons and the neutrons and trap the quarks and the gluons inside. And a residual effect of that is this attraction between protons and neutrons that keeps them all in the nucleus together. Now, a remarkable thing that we've learned is that there's a fundamental similarity between all these interactions, and they're all associated with elementary particles, basic interactions involving elementary particles meeting at a point in space-time. So the electromagnetic interaction is associated with two electrons meeting a photon. the gravitational interaction between electrons and the gravitational force between two electrons, let's say, is actually mediated by this fundamental interaction involving two electrons and a graviton. And if we concatenate these fundamental processes over and over and over again, we get all the processes that take place in the world around us. So electrons scatter off each other. In the simplest way, we imagine that they exchange this photon, that they excite a virtual photon out of the vacuum. But more and more complicated processes just come from gluing these basic fundamental interactions together. And something that was not obvious at all, but became eventually obviously true in the development of the famous standard model of particle physics, is that all of the interactions have the same structure. The strong interactions are associated with exactly the same basic interaction between quarks and gluons. The weak interactions are associated with exactly the same kind of pictures again, now with other kinds of cousins of the photon, W particles and Z particles. It's the same basic interaction. There are what from the fundamental short distance point of view look like detailed differences that make a very large difference when we look at physics at very long distances or concomitantly very low energies. For example, the photon is massless. And so if I try to excite a photon out of the vacuum, it's easier. It's harder and harder to make it to make an excitation that's relevant over very long distances, and that's why the electric force between electrons dies off as the inverse square law. Or if I have the graviton exchange, it would also die off as an inverse square law. However, it would be much worse if the particle was massive. It wouldn't just die off as a power law, it would die off exponentially. And that's what happens with the exchange of W and Z particles, which are massive. So that's why electromagnetism and gravity look like they're associated with long-range forces, because the corresponding particles are massless. But the weak interactions are associated with a short-range interaction of around 10 to the minus 16 centimeters. Another feature of these of the elementary particles is that they have spin, and the spin is quantized, like everything is quantized in quantum mechanics, and they come in multiples of 1/2 times the Planck constant. So the allowed spins that you can have just from quantum mechanics are any multiple of a 1/2 h bar. But the menu that we see, the electrons have spin 1/2, the W particles have spin 1, the photon and the graviton have spin 1 and spin 2, respectively. But the menu is extremely simple. All the familiar things that we know of just come from these three possibilities: 1/2, spin 1, 1/2, spin 1, and spin 2. Okay, so. And in fact, here is the menu of all the elementary particles there are and the basic interactions they have. We're not going to go through this table in any detail, but suffice it to say that this table really contains everything there is to know about the structure of the standard model of particle physics. We have quarks and we have leptons. The interactions are mediated by gluons, W particles, and W's and Z's, and the photon, which are sort of mixed together. The so-called electroweak interaction, and the graviton. And so this menu just tells you which stick figures you're allowed to draw, which basic 3-point couplings you're allowed to have, and the interaction with gravity is universal with the universal strength. Okay, so this particular set of elementary particles and interactions is what governs fundamental physics. Certainly down to the distances that we've probed so far, which is around 1,000 times smaller than the nucleus of the atom, around 10 to the minus 17 centimeters. Those are the distances that are being probed at giant accelerators like the Large Hadron Collider. And this structure holds sway all the way from there, and perhaps even much shorter distances, we'll come to that, all the way out to the size of the observed universe, around 10, 15 billion light years. Now, but what I want to get to is something more structural. I want to explain, why did it turn out to be so simple? Why are the fundamental? I mean, this might not seem terribly simple. This menu is not terribly simple, but it's certainly not extremely complicated. And it's remarkable that it all comes down to this basic simplest interaction with this tiny menu of spin. So that's what I want to now sketch an explanation for. Why do we only have simple fundamental interactions that involve 3 elementary particles meeting at a point? I told you that we concatenate these interactions over and over again to get everything there is, but why weren't there fundamental 12 particle interactions? That would, of course, make it impossible to explain, to reduce the complexity beyond beneath 12 particle scattering. Didn't turn out that way. We only have the basic interactions are just 3-point scattering, and all the other interactions are derivative from that. And why do we have only such a tiny menu of spins? And so what I'd like now want to sketch for you is an argument that in one way or another, people have known for maybe 40 years, but I think it's been increasingly appreciated with time. And as I said, it's not widely appreciated even for most physicists, never mind beyond physics. I want to, so what I want to explain is that whatever the ultimate theory is, which we don't know what it is, but so long as it agrees with the principles of space-time and quantum mechanics, it's guaranteed on general grounds that at long enough distances, you'll see a world described by some finite number of species of elementary particles interacting with a fundamental 3-point interaction, and that the only allowed spins are for elementary particles are spin 0, a half, 1, 3 halves, and 2. In other words, if you locked up sufficiently competent theoretical physicists in a room, you didn't let them see the world outside, you just handed them food and graduate students and the principles of space-time and quantum mechanics, they would discover that at first they would think it's impossible to make them consistent, but after they worked for a while, they would discover this very small set of possibilities. They'd also discover that this massive spin-do thing is unique, and that if there are massive particles around, it would make it go around in orbits. It's gravity, but they haven't seen gravity. They haven't seen Newton's apple fall. They haven't experienced Einstein's falling elevators. In fact, they would discover not only is it gravity, but that the theory that describes it has to be general relativity to some leading approximation. And they would discover that without knowing anything other than the principles of special relativity, space-time and special relativity, and of quantum mechanics. And I put in red here, so the familiar elementary particles that we know of have these spin 1/2, 1, and 2, but you see there are these interesting 2 other possibilities of spin 0 and spin 3 half that I'll say a little bit about.